Ever wondered why our daytime sky is that perfect shade of blue? It seems simple, right? But the real answer involves some incredible physics called Rayleigh scattering. So, what exactly is it? To understand this, we first have to look at sunlight. It isn't just white light. It's a whole spectrum. Red, orange, yellow, green, blue, indigo, and violet. When that full spectrum light source hits Earth's atmosphere, the journey begins. The atmosphere is made of trillions of tiny molecules, mostly nitrogen and oxygen. When the light waves encounter these particles, they don't just pass through. They interact. These molecules act like microscopic speed bumps for the incoming energy. This process is called scattering. Rayleigh scattering explains that the size of the particle dictates how light behaves. Specifically, shorter wavelengths, like blue and violet, are scattered much more effectively than longer wavelengths, such as red and orange. Think of it like this. If long waves are like big tennis balls, they tend to pass through the molecules largely undisturbed. But short blue waves act more like marbles. They encounter and interact with the tiny atmospheric particles much more frequently, bouncing off in every possible direction. Because blue light is scattered across the entire sky by these atmospheric molecules, in every direction and at every angle, your eyes receive a diffuse, uniform glow of blue. This constant scattering is why our daytime skies appear so vibrantly blue. If scattering is so powerful for blue light, why don't we see violet? While violet scatters even more easily than blue, the combination of atmospheric absorption and our own limited visual spectrum means that blue dominates what we perceive as the sky color. Now consider sunset. When the sun is low on the horizon, its light must travel through a far greater thickness of atmosphere. This long path acts like a natural filter, scattering away most of the shorter blue wavelengths entirely. So, to recap, sunlight is actually a full spectrum of colors. When it hits Earth's atmosphere, those tiny molecules, nitrogen and oxygen, act as natural scattering centers. They are much more effective at redirecting shorter wavelengths, like blue light, than longer ones. But what happens when we leave the atmosphere? In the vacuum of deep space, there are virtually no molecules to scatter light. Since nothing redirects those photons back to your eye, the sky appears absolute and perfect black. A stark reminder that our vibrant blue world depends entirely on this unique atmospheric interaction. This isn't just an atmospheric quirk. It's a fundamental rule of physics in action. From how sound travels through air, to the subtle polarization of light off water, physical principles govern everything we observe, a constant interplay of energy and matter that defines reality. The universe is full of these incredible mechanisms waiting to be understood. If you want to dive deeper into quantum physics and the rules that govern reality, hit subscribe and explore with us next time.